Welcome to another session of data analysis and visualization. So now we're going to come back to PCA. So after finishing this, I will spend a couple of minutes of whatever actually we have learned so far. So we mentioned two important things in PCA: eigenvector and eigenvalues. Eigenvalues, we said that in PCA, principal component analysis, we aim to project the input data set, including a high number of features or variables, into a limited number of new features or new variables, which we call principal components, in which they include as much as possible information, important information of original data set. So, and for instance, we mentioned this is axis X, axis Y, let's say two variables in input data set, let's say alcoholic drink and fresh potato input data set which we had. So, and then after projection, we got a new coordination system, which this new coordination system has one axis, this one, which we call principal component 1, PC1, and the second axis, which is in an orthogonal way, it means right angle with the first axis, principal component 2, providing the direction of most variation, first most variation and the second most variation of data. So we also actually mentioned that PCA can be used as a technique in which we call unsupervised learning. And as you remember, you may recall, for this case, for this input data set, Northern Ireland actually was rather different from other countries in the UK. So today we're going to actually look at some examples of R packages, as well as some visualization of results using some functions here. So for instance, here, principal component, I use this function, this package, purecomp, and as well as function. I transpose the input data set in which features are columns and rows are observation. So I got these four principal components, and then showing the principal components in two dimensions, PCA1 and PCA2, provided us these observation or samples, which we can see rather separated based on these two new principal components. And as you can see, I didn't use principal component 3 and 4, just in 2 dimensions. It shows that Northern Ireland is different or far away other countries. But the question is whether this illustration in 2 dimensions could really provide us correct visualization. So if we look at the 3D or 3 dimensions of this principal component, it means if I added principal component 3, so the story would be a little bit different in terms of interpretation. So again, I put it in this perspective, in this angle for principal component 1. If you look at this, this is the principal component 1 in this direction, principal component 2 the second, and the principal component 3 is the direction towards all of you. So X, Y, and 3, okay? So this is another angle of the result. So you don't need to provide the angle here. As soon as you get in the plot as a new window, you can drag your mouse in the plot, and then in different angles you can play with the image. Okay, so this is another angle that again which is rather similar. I put it just a little bit down the principal component tree, this direction. So if I actually just get rid of the ellipse here, you can see this is the Northern Ireland, this is the England, this is the Scotland, and this is the Wales. So again, this is, I again rotate this figure in 3 dimensions in clockwise, and as you can see, Northern Ireland, Wales, England, Scotland. The selection of the angle and creating the final result is really important for the interpretation. Okay, so I'll provide you more example to see how this works. Okay, so I again just get rid of this line as well by providing just dot Northern Ireland, Scotland, England, and Wales here by providing for this plot, just put it fancy false, and it's just get rid of the extra point. You can actually provide a bigger point and different coloring based on different sample or based on any groups that you already have for these samples. So we will work on this a little bit for other examples. So this is another illustration of the principal component using a function called pairs. Again, the pairs is a general function. So as you can see, I'm using x, the values of principal components originated from these object, and this is the 4 principal components. Each individual of this box shows 2 dimensions of principal components. For instance, for this one, it's the principal component 1 and principal component 2. You're always looking at the lower part of the triangle in pair result. Okay. If you remember, you have 220 is my favorite visualization. 220 samples with 17 features, and as you can see, these are samples from 4 subgroups. The coloring is based on the subgroup of each sample I had. So, but as you can see, component 1, 2, 3, and nicely you can see the separation of these samples. Okay, visualizing of these samples when I coloring according to their subgroup of these samples. Okay, this material actually published in Nature 2 years ago. Another package, very useful package in R is this one, Facto MineR, and you can use PCA again on your data set. This data set rows are individual and columns are numeric variables or features. You use 17, for instance, the data set has 17 features, and by printing the model, object model, you can get this result. Okay, so this package and PCA actually could provide you rather more data that you may work on this for better understanding of your data set. So by this object, by object PCA model input data set, and then using $eigen, you can access to the numeric values of eigenvalues. You can see the correlation between the features that you have using $variable correlation. You can also have the level of contribution of each variable or contribution of each individual or sample. So, or even you can get the weight or loading of each variable. Using this function, you can get loads of information here, okay? So we're gonna actually look at a couple of these. I mean, I put it in with underline and showing some of the result from running these values. So if we use the name of the object originated from running PCA and then $ig, eigenvalues, so you can get the eigenvalue related to the three principal components, okay? Do you remember what was the interpretation of eigenvalue? Again, we have the percentage of variance for this new axis or new principal component, and this is the cumulative percentage of variance for principal 1, 68. When adding principal component 2 is going to be 93%, and when we adding principal component 3 is going to be 100 variances of all data for these three principal components. Okay, so now we're going to see what would be the level of contribution of features or variables to principal components or these three axes, okay? We have a library called correlation plot or correlate plot, which we can get this contribution. Okay, so here I use the circle here to show and the size of the circle actually shows the level of contribution. The larger the value of contribution is, the more a feature contributes to the component. The larger and bigger. So in that case, if you look at the fresh potato in dimension 2 or principal component 2, we have a rather large contribution here, which is in dimension 2, while for dimension 1 and 3, there is no contribution. So even for the rest of them, almost every individual dimension has contribution with link to original feature. So we will come back to this contribution because it was just the illustration. So the question is, okay, what would be the purposes of this contribution? How can we use in our analysis? Yes. So this is really important plot when you're using principal component analysis and using this function fviz underscore ig, very odd name. So for this function, I'm using the object model originated from running PCA on input data set, add labels true, number of component 3, and the y limit axis is between 0 to 100. One dimension 1, 2, 3, PCA 1, 2, 3, 68, 24, 6%, which covering nearly 100%. Okay. So the question is, why I use just 3 principal components? We had 4 principal components. Why are we using 3 here? I'll give you 2 minutes to think about, discuss with your friends and tell me what is the answer. Why in histogram I use just 3? Let me see if other people actually, other students. Yeah. I mentioned 3 times. So because the total cumulative percentage of variance is 100% using 3 PCAs. I'm going to come back to a bigger size of data set and doing this similar analysis, similar visualization as well. So you work with 9,126 samples with 440 features. You're familiar with this data set, yes? So this is all type of cancer subtypes in this data set. And if you remember, here I'm just showing the number of samples per cancer. So for instance, we have 1,000 samples belong to this group, breast cancer. I'm going to just highlight here that the population of samples more belong to this category of cancer. Okay, just another thing that I think was it as part of your individual coursework, as far as I remember, we have 6 immune subtypes with this number of samples, and we had the characteristic of imbalance number of data across this immune subtype as well. Okay, so this is the sample distribution across immune subtype. So I'm gonna come back to this plot. So just for the clarification, we had 9,126 samples. I decided to originally split the data set, try to split the data set into 2 data sets, 80% of this data set versus 20%. Because I was planning to work on 80% of this data set and developing a model, etc., and then testing the created model using the remaining 20% of data set. That's why I use this as a unobserved data or test data set as part of validation for data analysis and machine learning techniques. So this 80%, as you can see, 80% of each class is not 80% of the whole data set. I use PCA to visualize and some further analysis. So as you can see, the dimension here, I'm not using just 3 PCA to see this histogram. This is PCA 1, PCA 2, 3, etc. And as you can see from this histogram, the dimension percentage of explained variances for the first one usually is the highest one, which is 18%, nearly 14%, 6%, 5%. So it means rather I can consider nearly 10 principal components in my analysis. So till here is going to be 50%. So definitely I have to consider in my analysis at least more than 5 principal components. And this is really important. Yes. Yes,
why does it matter that
yes.
PCA is getting with a third explained variance is close to 100%?
Yeah.
Like, why does it matter? Like, why can I not have it?
So this actually coming back to the further analysis that we're going to do. If it is just for the purposes of the visualization of the first 3 principal components, we're saying that, okay, this is the visualization of 3 principal components as much as we can, because we are just able to visualize in a 3D, not more. But in terms of the further analysis, sometimes we're using PCA for feature selection. Sometimes we're using the principal component analysis for as a main analysis in identifying the pattern based on the selection of number of principal components. So if I give you a clustering algorithm, okay, and ask you to cluster these samples based on a specific number of features, you're using that, okay, I'm going to use PCA, transform to and project into a new coordination system, let's say 20 new PCA, and then you're going to actually use these new features to your clustering system, clustering method. So if you use just 3 or 4, in that case, the clustering accuracy is going to be just based on this variation. However, if you're using more feature, it would be accurate clustering and better separation.
So each of these columns is like how much of the variation is captured by that particular dimension.
Exactly. So that's why considering the number of principal components in further analysis is depend on this interpretation. So it's really important that when you're generating a plot, as you may realize, generating a plot or graph, etc., by itself is really a hassle. More importantly, when you're going to use this result, you have to properly interpret and to communicate with these images. And by interpretation, it means getting some inference, some new insight on based on the analysis. Okay? So again, this is for 7,302, 80% of the original data set, and 440 features or genes, as you may be familiar with the signature group and its genes. And this is the most contributing features for each dimension. Okay? So again, I use just 5 dimensions to illustrate here because rather 50% of contribution based on these 5 principal components will be happening. For some of them, there is no any contribution in 5, maybe in 6, 10, etc. Okay, so this is the another one continuing of 440 genes or features. Again, first, second, and etc. Okay. Before going to next slide, so I'm going to ask you what the purposes of this contribution. How can we use in a real world from these plots? Just think about maybe 1 minute to see, okay, how can we use this contribution plot? As I mentioned, as part of feature selection in data analytics and machine learning, it's really important to see which features have not contributing or not contributing in our analysis. So PCA visualization, if you plot using the normal plot for the object, you can get all of these samples. But because you know that the immune subtype for each sample, if you coloring all the samples based on the last part of the string of your sample name, C1 to C6, you can get this plot. Is it a nice plot, do you think? Very messy, isn't it? It's very confusing. So, what about this one? If I use, again, pairs to illustrate these 7,000 samples, again, this is a simple illustration of variances versus number of components. And as you can see, we have a drop here after 5. So it seems that 5 components would be rather good. So here is PCA 1 to 5, and I'm going to just exclude the upper part. So if I color these samples based on the immune subtype that we know, so it's going to be rather better. So, and PCA 1, PCA 2, the same interpretation that we have, but again, it still is not what I really wanted to see in from PCA, and specifically for the module which called data analysis and visualization. Okay, so if I just focus on individually providing the plots for using PCA 3D, and just for the C1 immune subtype or subgroup, I can get this plot, this visualization, which is really nice, and from different angles, as you can see, PCA 1, PCA 3, PCA 2, PCA 1, 2, 3, and you can see I use an ellipse here covering 95% of confidence interval. Perhaps I could actually spend some time to explain the mathematical part of the confidence interval, but from different angles, from up, if you look at this, again, we have very nice, PCA 2 is towards us, PCA1 tree, and I also actually use a plane to show exactly this. So this is for the samples from second immune subgroup. Again using PCA 3D and just playing with these parameters to visualize nicely all these samples. So again, from up, this is from samples belong to C4 immune subgroup and C5. So as you can see, you may say that C5 samples belong to this immune subgroup maybe has something different from other samples, because in terms of the visualization of principal component, they are far from the center. So, and the beauty of data analysis and pattern recognition, which we are doing, are visualizing this and then interpretation. Okay, so I'm going to actually add up all of this to provide a better visualization when I'm using 3, 5, 6 together. Okay, so far you can imagine from different angles, if I was adding C4, C5, C6 together, would be something like this. If I using C1 and C2 together, which is rather mess, but better visualization. This is C1, C2, C3. From up, C3, C4, C5, C6, and C2, C3, C5, C6, and all samples in a plot, in a 3D using PCA 3D. So, but I individually actually illustrated all of this samples group from different immune subjects. Okay. So, if I put it in a nice way, by the way, this is part of my research that I've done. I'm working on a paper to hopefully send it to a good journal. So just because it's not published, I would like you all to just pay attention to not to share and distribute these materials. So (7,302 samples in just one slide, and with some interpretation, which is a part of my research in that area.